Good morning, student. In last lecture, we saw to express recurring decimal in P upon Q form, that is irrational form. In this period, we will prove root 2 is an irrational number. You find irrational and real numbers. Root 2 is irrational number. This can be proved using indirect proof. Let us assume that root 2 is an irrational number. Let us assume that root 2 is rational number. Here we consider or we take as an assumption root 2 is rational number. Then we prove our assumption is wrong. That is root 2 is an irrational number. Firstly, we suppose or we let us assume root 2 is rational number. So, root 2 can be expressed in P upon. So, root 2 can be expressed in P upon Q form. If root 2 is rational number, how do we write rational number? We know that in P upon Q we write rational number. So P upon Q is the reduced form of rational number. Hence P upon Q is the reduced or standard form of rational number. Reduced form of rational number. Hence P and Q, hence P and Q have no common factor other than 1. Have no common factor other than 1. We know that if we write P upon Q in reduced form or standard form, then P and Q have no common factor other than 1. So, what is our assumption? Root 2 is rational number. So, we write P upon Q is equal to, or root 2 is equal to P upon Q, because root 2 is rational number is our assumption. It is given. So, therefore, next step, squaring on both sides. So, x square on both sides. That is, square of root 2 is 2, and square of P is P square, and square of Q is Q square. So 2 is equal to P square upon Q square. Here P square is even. Therefore, we write this term in terms of P square. So P square is equal to, here Q goes to LHS of equal sign. So it becomes 2q square. P square is equal to 2q square. Here is coefficient of q square is 2. So it is clear that p square is an even. So therefore p square is even. If p square is even, then absolutely p is even. Therefore p is also even, means 2 is a factor of p. Give it 1. Number 1. So p is a factor of 2 is a factor of p. So we write p is equal to 2t, because 2 is a factor of p, and therefore p square is equal to 4t square, and t belongs to I. Small t belongs to I, and means set of integers. T is any integer belongs to set I. That is, t is any integer. We know the value of p. Value of p is therefore we take square on both sides. P square is equal to 4t square. Here we write 2q square is equal to 4t square, because we know that p square is equal to 2q square. Therefore, in next line we write 2t square, dividing by 2 on both sides. So we get q square is equal to 2t square. Here we get q square is equal to 2t square. Therefore, q square is also an even. Therefore, q square is also even. Therefore, yes, q is even. From the statement that is 2 is a factor of q. Check statement first and statement second. From these two statements, it is clear from the statement first and second, 2 is a common factor of p and q both. This is contradictory, because in p upon q we have assumed that p and q have no common factor except 1. In beginning, we see p and q have no common element other than 1. But here, from statement first and second, it is clear 2 is a factor of p and q both. So here is point. contradictory. So because in P upon Q, we have shown that P and Q have no common factor except 1. From the statement okay, 2 is common factor of P and Q both. This is contradictory because from the statement first and second 2 is common factor of P and Q both. But this is contradictory because in P upon Q we assume that P and Q have no common factor other than or except 1. Common factor except 1. So our assumption that root 2 is rational is wrong. Therefore, our assumption root 2 is rational is wrong. Therefore, our assumption root 2 is rational is wrong. Therefore, root 2 is irrational number. Therefore, root 2 is irrational number. Similarly, one can prove that root 3, root 5 are irrational number. So here hence we proved that is root 2 is irrational number. Similarly, one can prove that root 3, root 5 are irrational numbers. Numbers root 2, root 3, root 5 can be shown on a number line. The numbers which are represented by points on a number line are real numbers. In every point, a number line is associated with a real number, and every real number is associated with a unique point on the number line. We know that every rational number is a real number, but root 2, root 3, minus root 2, 5, 3 root 2, etc. are not rational numbers. It means that every real numbers may not be a rational number. Thank you. In next period, we will see decimal form of irrational numbers.